Welcome back to another stream. Yesterday we did the byte BPE or byte pair encoding, and we only did the actual programming, and there was a lot of stuff in here that I didn't understand. So that's the plan today, to tackle all of this. I'm starting the stream a bit later today. That's just how it goes sometimes, so hopefully we'll still have time to go through everything. But I might have to split this into 2 parts if it runs too late. I have to take my car to the inspection tomorrow pretty early. So I can't stream too late today, which is a bummer. But enough about that. Let's just get right into it by starting from the top, I suppose, because there's nothing here that I missed, right? We have... Let's read through this one more time to make sure that I've actually understood everything correctly. So, next up, exercise 9. Byte level BPE, byte vocabulary, 0 to 255. So the integers here is the vocabulary, plus the space token, which is integer 256. Here's a focus plan, plus starter you can paste straight into your sandbox, which we didn't do. We actually wrote everything. What you'll build. Train merges over bytes, not characters. Will still split on white space and prefix each word with a space token so merges don't cross word boundaries. Encode by replaying merges in order, left to right, non-overlapping. Decode by expanding token IDs back to bytes, and UTF-8 decoding, drop the very first leading space. And then we had export bonus here with the frequency ordering. Alright, then here from the imports, or the modules we're importing here, it says we don't use list. It seems to be a common trend with these scripts that ChatGPT is providing as examples, that there are modules or classes, variables in this case, that don't actually get used or aren't used correctly, or maybe it's just pylons that don't pick up on their use correctly, but they don't hurt anything being present, so I suppose I'm just going to leave them. Anyways, we have the space ID, which is a constant we set here to 256. Base vocab, byte 0 to 255, plus space token 256. And we have the function normalize. And we have the parameters, so string, the bool for normalization and the bool for lowering. And we only do a check for lowering, and we replace the text with a lowercase of itself, and then we return it. And that's all we do, since we want to avoid an NFKC for compatibility issues, I think, or maybe just to keep it stable. So I don't really know what an unstable byte would look like, but since the AI think this is best, then let's just go with it and not question it too much. So we only normalize with this function here, and then we have the words function here, which returns and should I say this returns a string here. But this function here has a parameter text, and it returns a list of strings. So it splits the text on all the white spaces. Punctuation stays inside words. To move my keyboard a bit. There should be good. And so we return only like we return a list with all the words or all the sections that are split by white spaces, even if they're not words. And then we have the function called text to byte sequences. And we have the parameter for text, and we want to return a list of integers. A list of lists of integers. Convert text to a list of word sequences of token IDs. Each word sequence starts with space ID, byte. So I suppose this is a byte. Maybe the byte value for 256. That's my guess, but I should probably ask the AI. Hey Rufus, what's the byte value of 0x20?
Sure, Andresk. So the hexadecimal value 0x20 corresponds to the decimal value 32. In other words, it's the space character in ASCII. So 0x20 is just a space.
So it's a hex character, not a byte character.
Exactly, you got it. It's basically a representation in hexadecimal form, but it corresponds directly to a single byte. So 0x20 is just a hex way of saying this is the byte with a value 32.
What is a byte even?
In a nutshell, a byte is just a unit of digital information. It's made up of 8 bits, and each bit can be either a 0 or a 1. So when we talk about a byte, we're just talking about a little chunk of data that computers use to represent things like letters, numbers, or symbols. So that 0x20 is just one of those bytes that happens to represent a space character.
But is there a way to like print out a byte on its own without converting it to a hex character or an integer?
Yeah, absolutely. You can basically print out a byte as a raw byte if you want to. In Python, for example, you can just create a bytes object and then print it directly. It will look a bit like a binary blob. It's not going to look super readable, but it's definitely doable.
And with a binary blob, do you mean like zeros and ones in a specific sequence, or?
Yeah, basically. When I say a binary blob, I just mean that if you print a byte directly, you might see something that doesn't look like text. It's just the raw data. So instead of seeing a nice hex number or a readable character, you might just see a sequence of bits or a little chunk of data that looks like gibberish. But that's totally normal, and that's just the raw byte form.
What would the raw byte form of 0x20 be? Can you say it?
Sure thing. So if you had the raw byte form of 0x20 and you just said it out loud, it would basically just be the space character. So it doesn't really have a sound beyond just being a space. It's silent, but if you think of it in terms of text, it just prints as an empty space. So that's all it is.
So the space character in byte format isn't composed of zeros and ones. I'm getting a bit confused here.
I get it. It can feel a bit abstract. So here's how to think about it. Under the hood, everything is indeed zeros and ones. When you see the space character as a byte, the computer is storing it as a series of bits. It's just that when you print it or look at it in a text form, it shows up as a space. But yes, behind the scenes, it's all zeros and ones. So hopefully that clears it up a bit.
Sorry, I was being so quiet. I was just thinking because it was kind of confusing and enlightening at the same time. And I think just like reading past this sequence here and getting down here kind of made it make sense to me, I think. As I understand it, then I shouldn't think of the bytes as like any data that I can actually like comprehend. I should just think of them like in some arcane form of information block. But we can also like match, like, let's say this hex number here to a specific byte. Even though I don't know what that byte is, I know that it represents this hex number, for example. So even though the space ID here says it's 256, this isn't the actual byte. It's like, because here we have in its token bytes, we have the base list here, or list of integers, where we loop through everything in the range of 256, and this will, or wait, will it? I was just thinking like it will loop through everything up to 255, and then we append like the white space character here, or the empty character, to the end of the base, like in the 256 spot. But now I'm a bit unsure if we start at 0, because if we start at 0, then we get 256 items. Let's ask. If I type 4i in range 256, will I get like, will that loop run for 256 times? From like where I is 0 to 255, or will it run with I from 1 to 255 and only run 255 times?
Yeah, absolutely. So in Python, if you say 4i in range 256, it's going to start at 0 and go up to 255. So it will run 256 times in total. Basically, it's inclusive of 0 and it stops just before 256. So you get that full range from 0 all the way up to 255.
I feel stupid. I just realized that it doesn't matter because we still have like bytes from 0 to 255. So there is already 256 integers in play here. It's just that I forgot about the 0, so yeah. This gets appended on the 257th position, or the integer number 256 in this case. Now this makes sense to me again, so that's good. Anyway, back to this here. We initialize a variable called sequences as a list of lists of integers. And then we loop through all the words, or should I say we call the words function here, which returns the split version of the text. And then we loop through all those separate elements, or all those words, and we create a variable called bytes, or a variable called b, that's for with the type of bytes, and we set that to the encoded version of the word, and we encode with the UTF-8. What's UTF-8 as an encoding specifically? Like, are there differences like UTF-9 and stuff like that? And what's the differences between them?
Yeah, so UTF-8 is a really common encoding used to represent text. It's super flexible because it can handle basically all the characters you can think of from different languages and symbols, and it does it in a way that's pretty efficient. There's not really a UTF-9 out there as a standard. UTF-8 is the big one that's widely used. There are other encodings like UTF-16 or UTF-32, which are just different ways of representing the same characters, but using a different number of bytes per character. But UTF-8 is kind of the go-to standard because it's backward compatible with ASCII, and it's just super commonly used.
Alright, so it's the default. Probably the one I'll always be using if that's the case. Anyway, then we have the initialized list or lists of integers here, and we append the I did look this up last time, with the asterisk here being like, it separates all the variable elements, I think, in this case. So this I'm trying to figure out, like, mapping it in my mind where these parts go, because if we append something, then we add to this list, so we add a list of integers. And the list of integers will start with this base ID, which is 256. And will continue with all these separate items in the byte, or integers in the byte. So wait, maybe I actually need to understand what a byte is, or will this like be 1 and 0, 1 1 0 0 0 1 1 0 0 1 1 0 1 1 0 1? Like, is that a byte? Because if it's like this, then all those elements would be like separated like this in the list. But and with the like, what's that? The no 0x20, like this with space character first, and then this is a list, and for each loop we add multiple of those. That makes sense to me, at least. And after that's done, we return the sequences. And here we have the function for init token, initialize tokens bytes. We want to return a list of lists of integers. Tokens underscore bytes ID, underlying byte sequence for the token. Or 2 underlying byte sequence for a token. So yeah, we have this range here then, which becomes 0 to 255. Or each list item becomes, but does this become like a list of only one item, or I feel like I need to have it like expanded for me. Break this down for me. I don't. Oh, whatever. So the range numbers 0 to 255, 256 values stops exclusive. Yes, this we know. For each I, it creates a list containing that single number. Wrap all those into one outer list. So base becomes a list of 256 singleton lists. Yeah, that was my guess as well, on my understanding. So we only get like lists with one item in it. Why singleton lists, not plain integers? That's my question exactly. In the byte BP code, each token ID maps to a sequence of bytes. For the 256 base tokens, each token represents exactly 1 byte. Its byte sequence is length -1, for example 97 for A. Later, when we merge tokens, we build longer sequences by concatenation. This only works cleanly if every token maps to a list of integers, bytes from the start. If base items were just I and int, concatenation would fail. mental model. Think tokens, bytes, token ID. List of raw byte values that token stands for. Initially, token bytes 97 equals 97. The byte hexadecimal or A. After a merge like 97 and 98, new ID, we define tokens new ID. 97 plus 98 equals 9798. Also known as AB as bytes. And we could do it like this. We could initialize base as a list. And then append lists of integers. Common gotchas, yes. There are list of integers. These are list of integers, not bytes. Not bytes objects. That's intentional, so we can easily list concatenation. So we can easily do easy list concatenation for merges. We later append the space token mapping separately. Yes, down here. Tiny REPL peak. This is so annoying. ChatGPT, no matter what settings you have, it like can't help itself from either taking my spoken words in English as Swedish, or writing in Swedish when it's strictly set to write and listen for English only. I don't know why it's hallucinating so much when it comes to language settings. It shouldn't. But shortly, this is a 256 length list where each element is a byte sequence, which makes it easy to build a longer token sequencer via combinations. I think I don't want to do translations. That's what AI is for. It should be able to do that on its own. Not require me to do it. Alright. So I think I've gotten that figured out. Then we have the pair type here. So we create a type called pair, which is a tuple of two integers. And a tuple is a constant string, or constant list, I think. I was gonna say a constant dictionary for a second, but no, a constant list. I think I should probably double check that. Is a tuple a constant list or a constant dictionary?
So a tuple is more like a constant list, in the sense that it's an ordered collection of items, and once you create it, you can't change it. It's immutable. So it's definitely not like a dictionary because it doesn't have key value pairs. It's really just a fixed ordered sequence of elements. So you can think of it as a constant list.
All right. So the next function here called count adjacent pairs. We have a sequences parameter for a list of lists of integers, and we want to return a counter of the tuple. So we initialize a variable called count, which is a counter of tuples. And we loop through all the sequences. And then all the words or no. All the characters is probably a more correct assumption here. So I, in this case, is iterating through the characters, and we check the length of this sequence. So the sequence is the word here. And we loop through all the characters up to, and we don't actually loop, we don't get to the last character. We only get to the next to the last one. Is that how you say it? Next to the last one. And then we count those. So we have the variable as an integer, and its pair with a +1. And then we return the counts when we've done that for all the sequences and all the, or should say all the words in the text. And then we have the function called apply merge to sequence. We want a sequence or a list of integers. We want the A as an integer, B as an integer, and new ID as an integer. And we want to return a list of integers. So we initialize the out variable as a list of integers, and then we set I to 0 and n to the length of the sequence. Then we loop, or should I say we, as long as I is less than the length of the sequence or word, then we, or should I say after that, we check if I plus 1 is still less than the length of the word and the current character equals the first character, or A, and the current character or the following character equals B. Then we append new ID, which is a parameter we supply, and we increment I by 2 steps. Otherwise, we simply append the sequence character in itself, or its ID, should I say, and we increment by 1 before doing it all over again until we've done it. No, we don't do it all over again. We only do this once. We go through the text and then we merge those pairs together, and if there are no pairs, then we simply append it on its own, and then we return the list of integers as the merge sequence. Give me a moment, I need to drink. Oh wow, my throat was really, really dry. I need to drink a lot more than I thought. And after this function here, we have apply merge to sequences. So we have sequences, which is a list of integers, and we have the a and b integers here and a new id integer. And we want to return a list of lists of integers. And oh, so this sequence or this function here calls this function, and it does it for each sequence. So this parameter will go through all the text with the a and b set here and new id also, since we return the result of all of this. And then we have the meat of the program here, the training. And we have the text parameter as a string and a vocab size as an integer. We want to return a dictionary for the model. So train byte level BPE on white space delimited words. It returns a model dictionary with tokens bytes as a list of integers, where token IDs is underlying bytes. Or token ID points to underlying bytes is probably a more correct way to interpret this. And merges is a list of integers in a learned order. And then we have this space ID as an integer here as well. So if vocab size is less than 257, then we raise an error because we can't train a model without having a vocabulary that extends beyond the base characters plus space. And we set tokens bytes to init tokens bytes. I'm not gonna lie, I'm still a tiny bit confused about why we append like this white space character, or should I say this hex character or hex value. I mean, is this like the universal byte for white space or something? If it wasn't, then it would be very strange. So it almost has to be like the universal character for it, but the other characters or the other byte values are integers. So it just feels strange to like append a hex value onto a list of integers. But anyways, we get the list of integers here, where each list will be a singleton list or whatever ChatGPT call it. And then we have the merges, which we initialize as nothing and as a list of integers. Start from raw byte sequences with space markers. So we set the variable sequences to text to byte sequences. And this is the function here that, right, encodes everything and appends space before. Oh yeah, because somewhere down in the program we probably already split the text. Or no. No, we split the text here. Wait a moment. So we split the text. And then we append everything. Okay, so yeah, we basically remove all the white spaces here. Or here. And then we append a white space at the start. Or the hex character for a white space at the start of each word or each sequence. And that becomes a sequence variable here. And then we have greedy BP loop. So while the length of token bytes is less than the vocab size. And token bytes is the vocabulary. And then pair count, which is a local variable here, we set to count adjacent pairs. And we pass along the sequence. Sequences even. We pass along all the sequences. And then we count them to see which one is the most common of all the pairs. And if we don't count anything, if there are no pairs, then we break the loop. Otherwise, we get the most common pair. Since this is a tuple, we can map it directly to the these two variables here that we set. So best A is the first tuple and best B is the second one in the pair. And then frequency here should be the count of how often these appear together. And this should be because we only want one number. We want the, like, or should say one tuple. Want the best one. And I don't know why we have 0 here. If we have a counter and then we have a dot most underscore common and then parentheses 1 and then square brackets 0 at the end, what does the 0 inside the square bracket do?
Yeah, absolutely. So when you call most common with a number like 1, it gives you a list of the most common elements up to that number. So in this case, you're getting the single most common element from the counter. Now that comes back as a list of tuples. Each tuple is basically your item and how many times it appears. So when you do the 0 at the end, you're just taking the first tuple from that list. In other words, you're just grabbing that top result.
So if we have parentheses best A, comma, best B, then outside the parentheses, comma, frequency equals pair underscore count dot most underscore common, parentheses 1, and parentheses square bracket 0. How does that work out?
Yeah, absolutely. So what's happening there is you're using something called tuple unpacking. So when you take that most common call and you grab the first element, you're getting a tuple that has basically two parts: the two elements that are the most common pair and the frequency of how often they appear. And then you're just unpacking that tuple into three variables: best A, best B, and frequency. So it just splits it up so you can use each part individually.
But where does the 0 come in? I mean, why is it a 0? Why isn't it a 1 or a 2 or a 3? Why is it a 0?
Yeah, absolutely. So that 0 is really just because you're taking the very first result from the list. In Python, lists are 0 indexed, which just means the first item is at index 0. So you're saying, give me the most common element and I want the first one. If you wanted to say the second most common, you'd use a 1 instead. But by default, that 0 just means the very first result.
And that is like the first instance in the list of most common items. Is that what you're saying?
Yeah, exactly. So that 0 is just picking out the very first item in that list of most common elements. It's basically saying, give me the top result. And that's the element that occurs most frequently. So yeah, you're spot on. It's just grabbing the very first one from that list.
That makes more sense. That makes so much more sense. Okay. I thought like because we only have one, we're only getting like a list of one, then I didn't like, my brain didn't pair these two like together correctly. If we had like, I don't know, like the top 5, then I think my mind might have automatically connected the dots. Like, okay, it's the first instance is in this list here, but since it's simply 1, then that didn't connect correctly in my brain. Anyway, after that's done, we have we check for the frequency. If the frequency is less than 2, then we break the loop as well, because we don't want to create one-off merges, because that's too infrequent to actually like, there's no point in training it on recognizing one-off instances. Because if they're unique, then there's nothing to go on. There's no pattern, I think. That seems like a logical conclusion to why you wouldn't want to do that. And as well, you would also like you would need a huge vocabulary to fit all of those as well. So, or practically an infinite vocabulary to fit them all, I suppose. Because at some point when you train it, you will get down to a vocabulary that consists of all the tokens you need. And going further would only like, or maybe not infinite, but there would be like a very, very large variation to consider. Moving on, we set the new ID to the length of tokens bytes. I mean, why though? know. Is it because... I mean, let's say this is the first one. Then the next ID would be 257. Since that's the length is 256 at the start. And we want the new token in that position, so that makes sense. And then we append tokens bytes append tokens bytes plus tokens bytes. Oh, we're grabbing the specific pair in question, and we're appending it together. That makes sense. And then we update the merges by appending this as a list as well, a list of 2 integers. And this has to be like the ID then, while this is the actual byte. Probably. And then we set the sequences to a list of integers. So say apply merge to sequences, and we pass along the sequences. And the first pair character and the second pair character and the new ID, which is the current length, or should I say the next item in the tokens bytes that we want to assign. And this goes through all the sequences, and we basically transform the sequence into an entirely new sequence by appending them, like by replacing the A and B with the new ID, or otherwise simply passing the information along. And then we return it, and here we return all of them. So the sequences, everything happens to this variable here. And then we create a dictionary, I think. Wait, yes, a dictionary. Curly brackets are for dictionaries. In this case, right here. And we set the token underscore bytes to token bytes, merges to merges, and space ID to space ID. So we basically straight up create our dictionary in the return section here. And then we have the function called save model. So we have the model dictionary as a parameter and the path as a string. We want to return nothing. And then we have with open path, And we have the path here as a string, W for write, and encoding as set as UTF-8 as F. Does this mean like I could likewise like do this and it would be the same thing? I'm not entirely sure, so it's probably best to get that cleared up. Break this down for me. Here's that line piece by piece. What it does. Open path opens or creates a text file at path for writing W. Writing W overwrites. Okay, so it's destructive. I think that's how you say it. Uses UTF-8, so all Unicode characters are written correctly on any OS. With as F, a context manager. Guarantees the file is closed even if an error happens. No forgotten f.close. Buffers are flushed properly. Okay. JSON.dump model f ensure ASCII false. Serializes the Python object model to JSON and writes it into the file object f. Ensure ASCII false. Don't escape non-ASCII characters. Write them as real characters in UTF-8. If true, the default every non-ASCII becomes, which is safe but less human readable. Okay. Why this combo? UTF-8 plus ensure ASCII false equals JSON that's human readable and round trips cleanly across platforms. That's good. Especially with non-native, with non-English text. For example, cafe or using with avoid resource leaks and partial writes due to unflushed buffers. So for example, a mini demo here. So we have a dictionary with a word and IDs. Oh, is this actually the... No, it can't be the correct bytes for the word cafe, can it? It would feel strange that C is in the position of 256, but... who knows? Pretty print for diffs. Indent 2. If you need a string instead of write to a file, use JSON dumps model. If you need a string instead of writing to a file. Note the S, yes, the S is missing here. Or no, it's not missing, it's... oh, JSON dumps model. I feel kind of stupid, but I don't really get it. I cannot get why you want to do it like this, other than the buffers being properly flushed, but I mean, like, this makes sense when it's written out like this, but I don't really know what this means, like, on a technical level. But I suppose that doesn't matter right now. We know that this works, or it should work. I haven't actually tested this model, but it should work. And then we have the load function here, which is the same but in reverse. We only supply the path, and we expect a dictionary in return. So instead we open path with R for read, is my guess. And we simply return the JSON.load with F as. I'm still like not understanding why you couldn't simply copy this and replace it with this here. There's something in the logic that's escaping me. All right. Let's move on to replay merges. So we have the sequences here, a list of integers, and the merges, a list of integers, and the new start ID. This is a new one. We want to return a list of lists of integers. Reapply merges in learned order. We don't need new start ID explicitly because we don't mint new IDs here. Merges map pairs to fixed IDs. AB to ID assigned during training, which is index in token bytes. During training, new IDs were assigned incrementally. We can infer them by doing this. Okay. For K, A, B in enumerate merges and enumerate object yields pair containing a count from start, which defaults to 0 with a value yielded by iterable argument. And merges is a list of integers. So for each list item, for each list of integers, this code segment is so condensed. There's a lot going on here. A lot of looping logic. I should break it down as well. Here we have it. This one here. Break this down for me. There's also a new function here for these thinking settings, so you can have standard thinking speed and extended. I'm thinking of like selecting the extended when doing when asking it for like the different exercises and then using the default when simply requesting answers. But look at this, like it's just throwing in Swedish here for some reason. It's gotten worse, I think. It's annoying. Let's unpack this trio. Okay. Enumerate merges plus tuple unpacking. Merges is a list like with this being the list and this being a list in that list. Learned in training order. Enumerate merges yields. Oh, okay. That makes sense. For K, A, B in does two things at once. K is the index. Oh, okay. And A, B unpacks the pair of that index into two integers, left and right token IDs to merge. That makes sense. But wait, is this actually a tuple? It says it's a list of integers. Is that a typo from me? Or no, it says list of integers here. I don't know if that's a dangerous type difference, but we'll see. For K, A, B, that's, A and B unpacks the pair at the index into two integers. So on pass 0. So on pass 0 you get K0, on pass 1, K1, etc. New IDs, new start. During training we minted new token IDs sequentially in the same order as merges. Base ID for raw bytes plus space ID. First merged got ID 257, next 258, then 259. When we replay merges at encode time, we reconstruct those IDs by index. If new start ID equals 257, then the kth, I don't know how to say that, merge gets 257 plus K. Oh, okay, that makes sense. That's also why this isn't like explicitly needed to pass along as a parameter. Or wait, yeah. And this guarantees the same token IDs for IDs the model learned during training. Sequences equals apply merge to sequences A, B, new ID. Sequences is a list of is a list of token ID sequences. Each word is a sequence. Apply merge to sequences, scans every sequence left to right, replaces each non-overlapping concurrence of A and B with a single token, new ID. We then assign the updated sequence back to sequences for the next merge in the list. Order matters. Merge 0 must happen before merge 1, etc. That's how BPE was trained. Tiny concrete example. Suppose base tokens are bytes and space ID 256. After training we have suppose base tokens are bytes and space ID. After training we have okay, so we only have those two merges and we ID 257, or it naturally becomes ID 257 since it's in that position of the list, and or in that position in the where do we have it? Token bytes. And encoding, we have a space as well. So this is the sequence. Oh, that's why we had 256 at the other example. Like this example here. Because we wanted a space. That makes sense. Pass K0. Then A and B 99 and 97. New ID 257. So the sequence becomes 256, 257, 102, 101 instead of instead of 99 and 97, we have 257 done as the ID. And on the next pass, we merge again CA and F, and then we replace 257 and 200 and 102 with 258. Now the sequence is shorter but decodes to the same bytes. Why this pattern? Determinism. Replaying merges in order with the exact same ID reproduces the training behavior. Non-overlapping merges per pass. Standard BPE applies one merge rule at a time, left to right, without overlapping replacements. Simplicity. ID reconstruction via new start ID plus K. Avoid storing an explicit AB ID map in the file. Common gotchas. If you change the base vocab or inserted special tokens with IDs above 257, you must adjust new start ID. Time complexity is roughly number of merges times total sequence length. It's fine for teaching. Production tokenizers pre-compute faster maps. Make sure merges is exactly the order learned in training. Shuffling it breaks encoding. All right. I'm gonna take a few minutes of break and just lie on the couch a bit and just process all this, as well as get some more to drink. So I'll be back soon. See you until then. And I'm back. Felt my head spinning as soon as I closed my eyes. I'm really tired. But I don't know. I mean, it's not that much left, is there? I mean, this looks like a lot, but it's the org parsing and stuff like that. We already done that several times, so I don't need to go through that with as much of a comb. And yeah, I think I'll manage to go through all of this today. Maybe not. We'll see. We'll see. So after replaying the merges, reapplying merges in learned order. Seems we are dropping frames still. I'm just gonna wait until my internet comes back in full force. Are we back? It looks like we're back. I dropped like 13k frames, so that wasn't great. Took a few minutes before the network reconnected. I don't know why, but it's probably my ISP. But it seems stable now. Let's just hope for the best and continue on. So, what was I saying? We have... I'm a bit confused about where we use replay merges. Is it used? Where is it used? Replay merges. It's literally in the next here for encoding. Oh, obviously we need to replay the merges on a new canon text to encode with it. That makes sense. That's why we're doing it. Okay, so the next function, encode text. Text as a string, model as a dictionary, and an asterisk as a parameter. I've forgotten why you have an asterisk as a parameter. What does it mean to have an asterisk as a parameter in Python?
Yeah, absolutely. So in Python, when you see an asterisk in a function parameter, it can mean a couple of things. If you put it before a parameter name like strargs, it means, hey, this function can take any number of positional arguments, and they all get mapped up into a tuple. If you use it on its own in the parameter list, it can also mean, after this point, all the following arguments must be keyword only. So it's just a way of controlling how arguments are passed into a function.
And what do you mean with keyword only?
Yeah, sure. So keyword only just means that those parameters have to be specified by name when you call the function. So if you've got that asterisk in the parameter list by itself, everything after it has to be passed like param equals value, instead of just being given positionally. It's just a way to make your function calls clearer and to avoid any confusion about which argument is which.
That's actually pretty neat and makes sense. So I suppose that's to not confuse which parameter is which, since they're both booleans. At least that's my guess as to why you do this. So we set the text to equal normalize, so we normalize it. And since we commented out the normalization, we'd only lower it, even though the function is called normalize. And then we set the variable sequences to text to bytes sequences. And here we go through all of the... Oh no, we provide the text and then we split the text into lists of strings, and then we loop through all those lists and we convert them to a new list, or should say we copy them to a new list and I append like the space character before it, and we encode it. I can almost see the order in front of my eyes. And then we take those words or those sequences and we combine them, I think. So here we return them as a wait. Oh, here we are. Yeah. So we convert them to bytes and then we append them to the new list here, which is a list of lists of integers. And then we set the merges to the model merges from the model we already trained. And we set a new start ID to 257, first ID minter of the base. Sequences equals replay merges of sequences, merges, and a new start ID. And so we basically encode it all, because that's all we do in replay merges. We only merge it all again. And then flatten into one stream of IDs. So we create a list of integers called IDs, and then we have this complicated loop here. And I'll need someone to break this down for me. Break this down for me. All right, so what it does: goal, flatten a list of lists into integers into a single list of integers. That's a mouthful. And sequences is so sequences, and this is a sequence here, one list per word. The comprehension reads left to right for each S in sequences, then for each TID in S, output TID. Result. Okay, so it's equivalent to, yeah, this is what I actually wanted to see. So it's like initializing a list called IDs and then looping through all the sequences and then looping through all the tokens. Oh, TID token IDs. And then we append that token ID. So it's a row major preserves the original order within and across sequences. Alright. And then we return this flattened stream of IDs. And that's our encoded text. So yeah, if we get this far, then we actually have like encoded text, but we also need to decode it somehow. So we have the decode function here, and we want the IDs parameter, which is we want it to be an iterable of integers, and the model that we trained. We want to return a string. So we set the tokens underscore bytes to the type of lists of integers and to the value of the token bytes we store in our model. And we set the out to a byte array. This is a new type of class we haven't worked with before. I'm not entirely sure, but is it simply an array of bytes? It might be. For token IDs in IDs, out.extend token underscore bytes TID. So we have the value of token byte to the token ID here. We extend the append all the items from the iterator or sequence to the end of the byte array. So this is kind of like list.append. is my guess. But instead, since it's a byte array, we do .extend. Then drop the first leading space if present. We prefix each word with space. So... oh, like the first space in the whole text. So if out actually has anything, and the first position of out is a white space, then we delete out, or we delete that white space. And when we return it, we return bytes out.decode UTF-8. So we decode the bytes array, and errors replace. I don't know what that means. But makes sense at least. But I should probably ask about the byte array. What is a byte array in Python?
Sure, so a byte array in Python is basically a mutable sequence of bytes. You can think of it like a list of bytes that you can modify. It's similar to a bytes object, but unlike a bytes object, you can change its contents. So you can add, remove, or modify individual bytes. It's pretty handy when you need a mutable buffer of binary data.
So it's the byte equivalent to a list, like out dot, or should I say, if we set out to a byte array, and then have a byte, disregard that. If we have a byte array dot extend, it's the same as a list dot append.
Yeah, you've got it. It's pretty much that idea. So a byte array is like the byte-based cousin of a list. And when you use something like extend on a byte array, it works similarly to a list extend. It just adds multiple bytes onto the end. So yeah, you're spot on.
But you don't actually extend lists, do you? You append them, right?
Yeah, that's a good patch. So with a list, when you add a single element, you use append. But if you want to add multiple elements from another list, you use extend. And it's the same kind of idea with a byte array. If you add multiple bytes at once, you use extend. So you're right. Append is for single items, extend is for multiple.
So you can use byte array dot append as well for single items.
Exactly, you can. So if you're just adding a single byte to a byte array, you can use append, just like with a list. And if you're adding a bunch of bytes, you use extend. So yep, it works both ways.
Well, that's neat. I hadn't thought about using append with a list. Or should I say like appending a list to a list, but I suppose like extending it would make more sense. Just like with as a vocabulary. But this makes sense. The decoding here is the errors replace here. I'm not entirely sure what this means. Is there a... oh. So this is a value. So we have strict here and replace is one. I don't know, maybe lenient is another, who knows. I don't know if this is important, so I'm just going to ignore it for now. And then we have the function called token bytes to string. So we have the token byte or toc bytes as a list of integers, and it returns a string. Printable token string for export. Decode as Latin 1:1 byte mapping, and replace literal space with J. So merges.txt is unambiguous. I don't know why you want to replace space with this character, but there has to be a reason for it. So s equals bytes, talk bytes dot decode with the encoding of Latin 1, and we return it by replacing white space with the G symbol. And then we have the export GPT-2 files function, which requires the model and the train text and the out prefix. Exports as in original order, stringify tokens, out prefix, frequency ordered token to ID mapping. Note frequency ordering is only for the export. So we have tokens underscore bytes, which is a list of integers, and we set that to the model of token bytes. And then we have the merges, and we do the same there. And then we create we have this here again. So we create an object called f, which is this. So we loop through merges, and merges is the list of 2 items, or the list of lists containing 2 items. And we set A and B to those merges. And capital A equals tokens to bytes to string, tokens to bytes. So we convert that to, or we decode it. Yeah, we decode it. I set it as a constant here and do the same for the other character. And then we use that object to write a formatted string with those characters, with a space between them. And then we do a new line after that one. And that's the merges.txt. So it will only be like 2 items in a list going down all the way. And then we have frequency ordered vocab on the replayed train data. So new underscore start underscore ID equals 257. Sequences equals text to byte sequences. Train underscore text. So this is basically the same as the training, or am I wrong? Where else do we do this? Text to... Yeah, in the training we do this as well. And also in encoding. So we set the sequences to the train text. And then it replaces the merges on itself. But it doesn't actually train anywhere, does it? It simply formats the sequences before doing before we replay the merges on top of that formatted. That makes sense. And then we set the flat IDs. We loop through the token IDs for sequence in sequences, for token IDs in S. Or set the flat IDs to the token IDs inside this loop here, in a list of integers. And frequency I use as a counter on the list of integers. Or the frequency becomes a counter object of the int type. And cover all tokens even if unseen. So all underscore IDs equals list range length tokens underscore bytes. So it's a list of the range of the length so the length of the token bytes is the length of the vocabulary. So this might be without any new words, and it's 257 with a space character as well. So if we say range here, then it becomes 250. Or it becomes, it's a return an object that produces a sequence of integers from start inclusive to stop exclusive. Oh, so it's a list of 0 to the max number, so that becomes like 257 in this case. Oh no, 256 in this. 256 in this case. But or maybe not. The length of token bytes should be 258 in that case, and the range 257. Or 0 to 257. That makes more sense. And then we sort the list with key lambda. Okay, this is one line I'll need some aid on. So wait, which one here? Break this down for me. Okay, so what the variables are: context, all IDs, a list of every token ID, yes, like I already figured out. And then we have the frequency, which is a counter / dictionary token ID, how often it appears after replaying merges. Oh yeah, frequency, yeah. How often it appears after replaying merges on the training text. Alright. How the sort key works. Key equals must return a value that Python can compare to order items. Here it returns a tuple. Oh, this is the first item then. This is the second one. Where frequency.get I and 0. Look up the count. Default to 0 if unseen. Unary minus. Flip the sign so higher counts sort first, since Python sorts ascending. Second element I, tiebreaker, smaller ID first when counts are equal. Because Python sorts tuples lexicographically, compare minus count, or should I say dash count, so bigger, no, minus count is probably more accurate here. So bigger counts come first. Okay. If equal, compare I, so lower IDs come first. Why not reverse through? If you did... Okay. You'd reverse both fields, making higher IDs win ties. We specifically want descending by frequency, ascending by ID on ties. Using count achieves that without reversing the tiebreaker. Or minus count. Or minus frequency in this case. Tiny example. Count 5, 5 to 10, 2 to 10, 8 to 3, 1 to 0. Oh, so it is minus. So we reverse... Wait... Yeah, we're literally reversing them. Sorted order by key ascending. Oh, we want a negative to make sure they actually show up in that order. Final, all IDs, 2, 5, 8, 1, high frequency first, ties broken by lower ID. And since the ID is 2 in this case here on this example, then it sets this as the first one. Gotcha/tips. If most tokens are unseen, they all get count 0 and thus sort by ID. Complexity is 0 and log n. Fine for worker sizes the low tens of thousands. That seems a lot still. Same patterns appears everywhere. Sort descending by X, ascending by Y. Descending by X, ascending by Y. Stop providing snippets in Swedish. Stick strictly to English. See if it saves this. Yes, updated save memory. I don't know why it hasn't. That should already be like in its memory since I've already set the settings to everything in English, but maybe this will make it work. Who knows? Anyhow, I'm still confused. I'm not gonna lie. I mean, what's even an unseen token? I don't know if we've even gone through that before. It sounds familiar, but only like peripherally. I'm gonna ask and see if there's a simple answer. What do you mean by unseen tokens in a byte pair encoding LLM?
Yeah, absolutely. So in the context of something like byte pair encoding for a language model, unseen tokens just means tokens that the model hasn't encountered during its training. In other words, they're new combinations of bytes or characters that weren't in the original training data. So the model just hasn't learned the pattern for them yet. And it might need to break them down into smaller pieces or handle them in a different way. So that's EULA means.
So unseen means that like tokens that the model hasn't seen during training specifically.
Yeah, that's exactly it. When we say unseen, we just mean tokens the model never ran into while it was being trained. So if it comes across those tokens later on, it's basically dealing with brand new pieces of data it hasn't seen before.
That actually clears it up a bit. But I mean, all IDs is this. We're only sorting it here. I don't really get what this has to do with the like handling the unseen types of tokens, but let's just move on and get to the last piece here. So build printable strings. Token_strings equals a list of token byte strings TB for TB in token bytes. We loop through token bytes, and for each item, which for each list, then we send that list to this function, which converts token bytes to a string and returns it. So we basically get a list of strings. Yes. And this function only decodes it and replaces this base with the G. Alright. And then vocab equals a dictionary of tokens, strings I, rank for rank I in enumerate all IDs. So the value of this this key it enumerates, so it enumerates all IDs, and the rank becomes the the order in the list of all IDs, and since we already sorted it, we get the rank. It makes some sense. So then the vocab would be like a dictionary with like I don't know, like CA, and then maybe given a rank with like, I don't know, 5 or whatever. Alright, and then we write to the file. So we have the out prefix here, and we have JSON dump. So we write this as a JSON file. We provide a vocabulary, and this is the object here. Again, I don't know why I don't like simply paste this here, but there has to be a reason. Ensure ASCII false. Indent 2. Indent maybe simply is for formatting purposes to make it look nice, but I don't know. And then we have the actual CLI or CLI, command line interface, and we have all the argument parsing and stuff like that. But I think I'm going to go through like this last stretch in the next stream, probably tomorrow, and then we'll also try this out, because I haven't actually tried this code out yet to see how it works and stuff like that, and I'm really curious. But that will have to wait, because I really have to prepare for tomorrow. So this is our all today. Hope you enjoyed it. Smash those buttons, and yeah, cheers!